The research paper investigates the equality cases of the Stanley Yan inequality for log-concave matroid inequalities. The Stanley Yan inequality, originally proved by Stanley for regular matroids and later generalized by Yan, is a fundamental concept in combinatorial mathematics. The paper addresses the open problem of finding equality conditions for this inequality, as posed by Stanley. For k equals 0, the authors provide an explicit description of the equality cases, extending Stanley's results to general matroids. In contrast, for k is greater than or equal to 1, they prove that the equality cases cannot be described explicitly, unless the polynomial hierarchy collapses to a finite level, which is a significant finding combining combinatorial and computational complexity techniques. The authors employ combinatorial atlas technology to prove the Stanley Yan inequality and explore its equality cases. They establish non-vanishing conditions for the inequality, providing a complete description of the equality cases for k equals 0. The problem of determining whether the Stanley Yan inequality is strict is shown to be unlikely to have a polynomial time verification algorithm, unless pH collapses, whereas the equality case for k equals 0 is in CONP. The authors further prove a theorem that provides non-vanishing conditions for all k is greater than or equal to 0, which has implications for the complexity of the problem. They also present a corollary establishing a connection between the inequality and log-concave sequences, and prove a theorem that provides total equality conditions, resolving a conjecture by Yan for loopless matroids. A counterexample to the conjecture is presented for binary matroids. Finally, the authors discuss the connection between the Stanley Yan inequality and counting spanning trees in graphs, presenting a theorem that bounds the relative version of the tree counting function, which is crucial in the proof of the main result. This problem is of independent interest and is related to the combinatorial problem of finding the smallest number of vertices in a planar graph with a given number of spanning trees. The research paper discusses the Stanley Yan inequality and its variations, focusing on the equality cases and their implications. It begins by highlighting the importance of the Stanley Yan inequality, particularly its stronger form, Theorem 1.13, which proves the existence of a planar graph with ln edges and exactly n spanning trees. The section also delves into the historical background of log-concave inequalities, including the work of Maclaurin, Newton, and Stanley, and their connections to negative correlation and combinatorial complexity. The paper then discusses the Stanley Yan inequality, which is a general matroid result proved using Lorentzian polynomials. This inequality is a significant extension of earlier algebraic and analytic notions, implying the ultra-log-concave inequality conjectured by Mason. The authors have also introduced a linear algebra-based combinatorial atlas technology, which includes Lorentzian polynomials as a special case, and used it to establish correlation inequalities for the numbers of linear extensions. The summary also touches on negative results, particularly the computational complexity of equality cases of combinatorial inequalities, highlighting the surprising development that for k is greater than or equal to 2, the equality conditions of Stanley's Poset inequality are not in pH unless pH collapses to a finite level. The research paper discusses the properties of matroids, including their representations over fields, and their applications in combinatorial optimization. Matroids are introduced as a pair of a ground set and a collection of independent sets, satisfying the hereditary and exchange properties. The direct sum, deletion, and contraction of matroids are defined, along with their representations. The paper assumes familiarity with computational complexity and recalls standard complexity classes. It focuses on the bases ratio problem, which is the problem of computing the ratio of the number of bases in two matroids. The main technical lemma reduces the bases ratio coincidence problem to the equality Stanley Yan inequality problem. This reduction involves constructing a new matroid with a binary representation and applying the deletion-contraction recurrence. The paper also explores the connection between spanning trees and continued fractions, introducing a novel theorem that establishes a relationship between these two concepts. The construction of a planar graph with specific properties related to its spanning trees and continued fractions is demonstrated, leading to the recursive production of graphs with desired properties. Here is the combined summary of pages 13-16. The paper extends the Stanley Yan inequality to sums of two continued fractions, presenting theorem 5.3, which states that for given integers a0, as b0, bt is greater than or equal to 1, there exists a connected loopless bridgeless planar graph G and an edge E element of E, such that tau G E equals a0, a1, as plus 1, b0, b1, bt, and E equals a0 plus as plus b0 plus bt plus 1. The proof relies on lemma 5.4, which constructs a new graph G by combining two given graphs G and H, preserving connectivity and planarity properties. The paper then focuses on counting spanning trees, aiming to prove theorem 1.13 and lemma 1.14. The proof of theorem 1.13 relies on theorem 6.1 by Larcher, which provides estimates on the distribution of GCD, D, M, equals 1 in M. By applying this theorem and planar duality, the authors construct a planar graph G and edge E, such that tau G E equals n, D, where D is an integer coprime to n, and E, G, is less than or equal to 1 plus C log n log n. The authors generalize the result to arbitrary n using the prime factorization of n and constructing a planar graph G as a union of bicopies of smaller graphs Gi, each corresponding to a prime factor pi of n. They provide number-theoretic estimates, including proposition 6.2, which states that for coprime integers a, b, there exists an integer m less than b, such that s, m, a, and s, bm, a, are both bounded by k, log a, log a, squared. The paper proceeds to the proof of lemma 1.14, involving the construction of an injection to prove the bounds. The verification of matroid basis ratios is then discussed, including the setup, the verification lemma, and the proof of lemma 7.1. The proof involves simulating the decision problem basis ratio verification with an oracle for basis ratio coincidence. Finally, the process of verifying the matroid basis ratios is detailed, including the construction of a graphical matroid and the use of the dual graph to establish the ratios. The research discusses the Stanley Yan inequality and its implications in matroid theory, focusing on the basis ratio problem as FARD. It begins by proving theorem 1.2, establishing the hardness of the basis ratio problem through a series of lemmas. The authors then utilize this hardness result to demonstrate the inclusion of NP in PP, bridging the gap between two major complexity classes. This is a significant contribution to the field, shedding light on the relationship between these classes. The section concludes by highlighting the importance of combinatorial atlases in proving theorem 1.3, a key tool in this research. The paper also discusses the concept of combinatorial atlases, a framework for studying log-concave inequalities in combinatorial optimization. It introduces the sequality property and the local global equality principle, which states that certain properties of a combinatorial atlas ensure that functional targets satisfying the sequality property will also satisfy the same property with the same constant. The authors construct a combinatorial atlas and define the matrix C, M, R, A, which is non-negative and symmetric, with diagonal entries equal to 0. This matrix is crucial for the proof of theorem 1.3, the main result of the paper. In the context of matroid theory, the construction of a combinatorial atlas A, M, R, A, is presented, where M denotes a matroid, R is a set of non-loop elements, and A is a scalar. This atlas is defined with an acyclic graph gamma and linear algebraic data. For each vertex V equals X element of omega 0, the associated matrix is C, M, X, R, A-1, if X is not a loop of M, and 0 otherwise. For V equals T element of omega 1, the matrix MV is a linear combination of C, M, R, A, and C, M, R, A-1. The linear transformation T, ang bracket left X, ang bracket right associated with the edge, V, ang bracket left X, ang bracket right, is the identity map. Properties of the constructed matrices, such as support and irreducibility of C, M, R, A are discussed. The atlas A, M, R, A satisfies properties like in, idem, and tinv, and under certain conditions, it also satisfies dex up. The paper then delves into the Stanley Yan inequality and its equality cases, focusing on the hyperbolicity of the constructed atlas. The proof of the equality cases involves a detailed analysis of matrices and their properties, including the support of the matrix and its relation to the set of non-loop elements. The induction step in the proof includes the direct sum of matroids and the rescaling of rows and columns. The authors conclude by verifying all conditions in Theorem 9.3, ensuring that every non-sync regular vertex in the graph is hyperbolic. This technical and complex proof contributes significantly to the field of matroid theory and its applications. The research paper focuses on matroids, specifically the Stanley Yan inequality and its implications. It begins with a lemma establishing a relationship between the matroid's rank and the inequality's parameters. This is then used to prove a theorem demonstrating the equivalence between two sets of conditions, involving the matroid's parameters and the inequality's parameters. The paper also delves into discrete polymatroids, discussing their definition and properties, including a theorem establishing the equality between two discrete polymatroids. The section on total equality cases of the Stanley Yan inequality explores the relationship between conditions E and IV in Theorem 1.9, including counterexamples and the generalized Mason inequality. This involves examples of double and linear matroids, as well as the log-concave inequality derived from substituting the direct sum M into the Stanley Yan inequality. The paper's technical aspects, including mathematical equations, algorithms, and specific terminology, are highlighted throughout. Here is a combined summary of the 4 pages. The authors explore the realm of matroid theory, focusing on the Stanley Yan inequality and its implications for combinatorial and computational complexity theory. They introduce a generalized Mason inequality, extending Mason's log-concave inequality, and demonstrate its connection to Lorentzian polynomials. This new inequality is derived using tools from computational complexity theory and is a natural extension of Mason's log-concave inequality. The significance of matroid theory is highlighted, particularly in the context of computational complexity, where understanding the computational complexity of matroid invariants is crucial. The authors discuss various open problems and conjectures, including the computational complexity of equality cases for matroid inequalities, which they believe to be NP-complete for binary and bicircular matroids. The paper delves into the connection between the Stanley Yan inequality and computational complexity, shedding light on potential limitations of what can be known about matroid inequalities. The authors discuss conjectures related to the Stanley Yan inequality, such as the possibility of two SPANNINGCIRCUIT being NP-complete for binary matroids. Lorentzian polynomials are explored as powerful tools in proving results beyond elementary combinatorial means, highlighting their significance in understanding the geometry of combinatorial objects and connections to algebraic geometry and representation theory. The concept of linear extensions of finite posets is also discussed, providing insights into the complexity of counting coincidences and other combinatorial problems. The paper touches upon homogeneous multivariate polynomials with the half-plane property, essential in various applications across mathematics and computer science. These polynomials have been used to establish numerous combinatorial identities and inequalities, including the celebrated Kohn-Sachs inequality. The pages 33 to 34 of the research paper delve into various aspects of matroid theory, including the Stanley Yan inequality, balanced matroids, and the Tutte polynomial. They also explore computational complexity, particularly the hardness of computing the Tutte polynomial and the complexity of certain algorithms. The referenced papers cover a broad range of topics, from the complexity of computing the Tutte polynomial to the hardness of certain problems in combinatorial optimization. The authors emphasize the importance of understanding these complexities in the context of matroid theory and its applications. Additionally, they highlight the role of computational complexity in determining the feasibility of solving problems in this field.